Welcome back, OChem 2. I am so excited. To share one of my favorite topics with you guys, and that is amines. I know it's the end of this semester and we're all feeling just a little bit of pressure, but what's awesome about this topic is that we panic, but you know what? We've put our time in. We put in our foundation, OChem 1 and OChem 2, and it turns out that with our amines, man, we've seen them all before. So even though it's the end of the semester and we're kind of freaking out, this is a smaller topic because we've actually seen these reactions a lot before. So let's take a minute and just have some fun. Let's enjoy the fact that we're at the end of this semester, and let's talk about one of my favorite classes of amines, and that is our alkaloids. Our alkaloids actually have a rich history. I know a lot of you are aiming for our bio and in our biochem next, and our certain medical professions and all kinds of things. And what's really interesting is that alkaloids have a phenomenal history in medicine and in something called natural products and natural product synthesis. In fact, since really 2000 BC, we as humans have combed nature for medicines. And some of those original medicines came from plants, and they actually contained alkaloids. So our whole study and idea of alkaloids has been around, for thousands of years. We're not talking 100 or plus years. We're talking thousands of years. That's pretty phenomenal. Even just for a couple hundred years, we're hitting things like morphine. Did y'all know that morphine is actually an alkaloid, and morphine itself has been around since 1800? Can you believe that? Our alkaloids, the original definition, they were plant-based. So let's go ahead and define an alkaloid. An alkaloid originally was an amine coming from nature and something that was isolated in a plant. Now, the actual version of alkaloids, that definition has grown and it has changed, and we're going to keep the nature part, so our alkaloids are natural products. We're going to keep the amine part, but we've actually grown to see that we don't have to have just plants. In fact, there are a large number of alkaloids that come from marine sources, and marine sponges is a whole area of alkaloids in there. And we've got also, in more recent terms, stereocenters. So if you were to ask a natural products chemist, they'll likely tell you that an alkaloid is a natural product that contains an amine and a stereocenter. If we look at our little Wikipedia link here, they may or may not contain a stereocenter. So our actual definition of the alkaloids has kind of changed, but there are likely thousands of alkaloids out there. They all seem to have biological activity. That means that they are doing something in bio and in humans and in nature, which makes them obvious targets in medicine, which is pretty cool. And they range the span of things like strychnine, so they can be poisons and toxins. They can come from the poison dart frog. In fact, that's my background. I made some compounds close to the poison dart frog. And all the way to things like morphine. There are a huge family of alkaloids that encompass at least one famous alkaloid that you've heard of, and that is LSD, but it's actually a very large family of alkaloid natural products in that. So it's just a rich history, an awful lot of classes of compounds that then have turned into medicine, and all of them have started with nature. So it's actually just an awesome place to end our semester with. It's really fun. Really fun. And then what's even better is we've already put our time in. We put our prep work in. So in fact, let's take a minute to look at where we've already seen amines. It seems crazy, like, oh, it's the end of the semester, we should be doing some ridiculous chemistry. No, we've already done the ridiculous chemistry. Let's take advantage. All right, where have we already seen amines? Believe it or not, we've laid this foundation since the beginning of OChem 1. Some of our first reactions together, we actually made amines and precursors to amines. So let's start with just an SN2. Let's take cyanide. We just did this in our last unit. What? It's like 2 for the price of 1. We're about to repeat. All right, let's do that SN2. And we could have any kind of solvent here, polar aprotic. All right. And then we saw in our last unit, well, you can reduce that, something like LAH, and now you're going to make that amine. Okay. Awesome. Just remember, you add a carbon. We just learned that in our last series of videos. And then did you ever wonder why in OChem 1 we turned right around and did the same reaction but with a funny looking reagent, and that was our sodium azide? Didn't that seem so random way back in the beginning of OChem 1? Like, what in the Sam heck is this, and why do I care? Well, when you take that really excellent nucleophile, that azide is a great nucleophile. You got a negative charge and it's small and it's like a little torpedo, very linear. Well, it turns out you can also reduce an azide and make that primary amine. And now this time we didn't add the carbon. Oh, shut the front door. All right, so what's the difference between these two? In this one, you're adding a carbon. In this one, you're not adding a carbon. You can go right from that azide to that primary amine. All right, now, both of these amines are primary, meaning we have only one alkyl group on there and 2 hydrogens. So we've actually seen this chemistry. We don't even need to draw the mechanisms for those. We already have. That's kind of awesome. So what if you actually wanted to make an amine, but you had something else in your substrate that would react with LAH? Okay, we saw LAH all the way back in Unit 2. We are very familiar with LAH, or lithium aluminum hydride. You know, that can reduce all kinds of functional groups, like our ketones, our aldehydes, our esters. So what if you're getting more complicated in some of these alkaloids, and you don't have just an amine, you have other functional groups? Okay, oops, hit the wrong thing. What if you have other functional groups? Well, now you're sort of screwed, right? Because LAH is likely going to react with it. It reacts with so many functional groups. So quite a while ago, this is a good historic reaction for us, a chemist named Staudinger developed a nice, gentle way to reduce these azides to an amine. Okay, notice we're making the exact same product, only this time we're going to use triphenylphosphine. All right, now what's the main difference? Well, the difference is now we're not going to have the same competition with other functional groups that we have with LAH. So I've included a link here for the Staudinger reaction. You could tell it's been around for a while. We've got several links if you want to check them out. My personal favorite is this cute little named reaction website. They do a nice job. They give you a nice little summary of that Staudinger reaction and show you the mechanism if you're interested. It is a reduction, so we still end up making that primary amine. Okay, I love it. All right, so with this chemistry, again, we're actually just repeating stuff that we've already seen. This is brilliant. Okay, what else did we see SN2-wise in our OChem 1? Well, actually, if you remember, it may have been buried on your nucleophiles list, but ammonia is actually a nucleophile. And now this reaction has been around forever as well. The problem is it is too good of a nucleophile. So there's good and then there's too good. What do I mean by too good? Well, sure, you're going to make this, but this is also a good amine and a good nucleophile. So, well, we can also, nobody says you have to stop there. If that reaction is a good nucleophile, well, why can't the amine that you just made be a good nucleophile as well? So let's go ahead and take that little lone pair, and we can do that again. And now we can make that secondary amine. So now we've got a secondary amine, primary amine here. Okay, well, if this one is good as well. So nobody says you've got to stop now. So we can now, holy crap, do that a third time. And then shut the front door, wait for it. Nobody says you have to stop there. You still have a lone pair on your nitrogen. So in fact, you are going to get one large mess until you use all of those lone pair. And you will in fact get a competition and you will make all of these. And if you've got a lot of your ammonia and your alkyl halide floating around in here. Oop, I hit the wrong thing. I meant to highlight. So if we've got plenty of our alkyl halide floating around, which you tend to make that reaction go pretty well, well, what's awesome is that you're probably going to prefer this one. Believe it or not, that lone pair on nitrogen is such a good nucleophile. You'll go all the way to that salt at the end. These are actually pretty straightforward to make. So you can make the tertiary amine. You can also make that quaternary amine. So is this a good reaction? It's kind of too good because now you're sort of stuck. You've got this salt. Okay. Awesome. So what if you really just had in your heart that you wanted to make a variety of amines? Well, so far we haven't really gotten there. If we just add ammonia, that's kind of a hot mess. If we're using our SN2 chemistry from OChem 1, boy, these work awesome on primary. They work okay on secondary, and they don't work at all on tertiary. Remember your OChem 1, you don't do SN2 chemistry on a tertiary. So we're not quite there for a variety yet. Let me show you two more reactions that you've actually already seen to make amines. We've seen them this semester and your OChem 1. And then let's hit our two new reactions, which are actually still repeats, can you believe it, to make amines and get selective. What if you want to make a secondary amine? What if you want to make a tertiary amine? All right, so we've actually seen aromatic amines already. You made this nitrobenzene in OChem 1, and you learned that you can reduce this with a variety of metals. There's several metals. You can also use iron or tin. There's lots of ways to do this reduction. And now you can make aniline. You make the amine that way. So this is another OChem 1 reaction to make an amine. Now, what about our last unit? We actually just learned that you could take an amide and reduce that with LAH and make an amine. Okay, well, awesome. All of these are great ways to make amines, but they don't necessarily give us a nice substitution on our amines. So let me show you two new reactions that are parts of things that you've already seen before to make amines. And we're going to end with the big ticket item. So our first new reaction is called the Gabriel synthesis. It's actually been around for quite a while. I've got a million links here for you for that Gabriel synthesis. But it's actually just fun to look at because it's chemistry from our last unit. We're going to go in reverse, essentially. This is so cute. So I'm going to take this funny looking aromatic compound, and this is a phthalimide. Okay. And if we take this and actually treat it with base, you can deprotonate that imide. So let me kind of draw this in a sequence. Remember, we can do this either way, like this. Or we can show that nitrogen now has 2 lone pairs and a negative. Now if we put in any alkyl halide, okay, now but the trick is it has to be primary. This only works on primary. Now what's going to happen? An SN2. And where is that nucleophile? It's your nitrogen. So now whatever your group is, you've just added to here. Okay, so this carbon right here is now right here. I love it. Okay, but wait a second. This doesn't look anything like an amine. Where am I going with this? That's crazy. How are we going to get an amine out of this? What? Come on, Unit 4. We are going to hydrolyze that whole thing. And guess what happens when you hydrolyze an amide? This is like an amide, just even more reactive, a little bit sassy there. It's an imide instead. What happens when you hydrolyze that imide? Well, look what happens. I'm going to make carboxylic acids. I don't even need to draw it. That was last unit. So I just made the carboxylic acids. And what happened to your nitrogen? Aha, you just lost it as a leaving group. And it turns out it's a great way to make primary amines. So that is our Gabriel synthesis. But again, it only works for primary amines. So far, we've seen a ton of ways to make amines. All of them in some version. We've seen parts of those before. Look at all these great amines. All of them were an awesome way to make primary. We had 2 of them that we could make a secondary okay. But here's where this falls apart. No tertiary and no selectivity. Okay, what does that mean? So if I wanted to make an amine that actually didn't have the same groups on it, how in the world would you do that? Okay, let me show you what I mean. So what if we wanted to make something like an amine like this? And okay, now, holy crap, out of all the methods we've looked at, none of them will let you make a tertiary, let alone a tertiary that doesn't have symmetry. It's not symmetrical. You've got 3 different things on there. So even though we've got a whole plethora of ways to make an amine, none of them will actually let you make very selective or not symmetrical or tertiary or various groups on there. There's really no variety there. You've got a whole lot of primary amines, a little bit of secondary, but nothing like this. Okay, how in the world are we going to make this? Well, the secret is actually chemistry we've already done. We're just going to add a step to it. It's called a reductive amination. Okay, now watch this. What would happen if I take this compound, okay? And I treat it with amine or ammonium chloride. We saw this back in Unit 3. Picture Unit 3 in our equilibrium, and let's lose water. And what do you actually make? Well, this was the perfect recipe to make an imine. Now, in Unit 3, we stopped there, and we recognized that equilibrium. We kind of stopped there. But you don't have to. You can add in something that will reduce a ketone, or an aldehyde will also reduce an imine. Although for this chemistry, you can always spot it because they tend to use a very specific version of sodium borohydride, and that is sodium cyanoborohydride. Okay, this is usually, you only see this with imines and a reductive amination, and what it does is it literally reduces that imine bond and it makes the amine. That's why it's called a reductive amination. But here's the kicker. Okay, so you make the first one. Well, then what happens if I do this again and I add formaldehyde? Done. Add formaldehyde, add your sodium cyanoborohydride, and now, hang on, I just wrote a 4 there instead of a 3. And now, holy cow, what did I just do? I just took this nitrogen. Okay, it already had this on it. Well, now I just made it into an imine of formaldehyde. That is not a positive. That is just a lone pair. So I've just made this imine, and then we're going to reduce it with our sodium borohydride. So let's put that in 80s air quotes. That's not going to last. So now what have you made? You have just made this. Okay, wait a second. Hold the phone. You just made a secondary amine, and you were in charge of the 2 groups that you could sequentially add to your amine. So we made an ethyl side chain first and then a methyl, and now in the lab, literally you're in charge with your sequence of alkylation reduction. So what if I want to complete this synthesis and I want to make the one that we drew? Now what would we add to this? We would add, I think we added an isopropyl there, we would add a nice acetone to this, and then we would add our sodium cyanoborohydride. And now we would add that. And now we just made a substituted tertiary amine with 3 different groups on it. So this is awesome because we actually have seen all of these steps before in our amines. We just haven't focused on the amine part. We've focused on the other stuff. So how do you make sassy amines? That's the beauty of it. You got one way. If you're going to make a primary amine, shoot. It's dealer's choice. You got 5 or 6 ways to do that. But if you want to make a substituted amine that may have 2 or 3 different groups on your amine, the only way you could do that is a reductive amination. So imagine how powerful this is if you take a reductive amination and you mix it with something like our manic reaction from Unit 3. Oh my word, you could make some really awesome amines that way. And in fact, this is what Mother Nature does for things all the way from alkaloids from the poison dart frogs to alkaloids in plants that can be quite toxic. If you've heard of the movie and the book Into the Wild, the young man that dropped out of college and took his journey up to Alaska, an alkaloid that is a nice tertiary amine was what he ended up eating in nature, and he didn't survive. So all of these methods, in fact, Mother Nature actually uses their version, Mother Nature's version of a manic and reductive amination. This is how we are going to make substituted amines. So as soon as you spot one in a synthesis anywhere, there's really only one way to make them, and that is your imine and then your reduction. So awesome. I hope this was at least fun. I know the end of the semester gets a little bit busy, but if you believe in me, you'll see that, gosh, we've actually seen all of this before. We didn't just spell it out as an amine before. That's it. Not too bad. Awesome. So I am going to stop this video, and then I'm going to turn right around, and we're going to